Welcome back, everyone. In this video I'm going to try and establish an intuitive understanding in this Veritasium problem, why current flows after just the transit time of light from the source over to the load. And I'll start by addressing a couple misconceptions I've heard in some explanations that I think warrant addressing, and then I'll kind of dive into the explanation that I have to give. And this is kind of in tandem with a video that I'm releasing as well that goes into the results of this new simulation, basically just larger and simulated for longer than the very first video I did. And I simulated a few extra things. Here you can see there's a wire here that's disconnected, so if you're interested in seeing the results of the simulation, you can watch that video. I'll have the link in the description, or you can find it on my channel page. So what I saw a lot in some comments or even in other people's videos was kind of this explanation that the current that starts from the source when the switch closes will induce a current in this wire and in the load connected to that wire, because when the switch closes, right, you've got this changing current, right? It goes from 0 up to some value, and therefore you're going to have this changing magnetic field, which will propagate over to this wire and induce a current. And while that is true, of course, we know generally how and that induction does work. That's how transformers work. That doesn't fully explain the current we see, because we now know that there would be kind of a quasi-steady-state current in the load that stays steady for the time that it takes the electromagnetic field to reach the end of the wire and bounce back, and then it steps up, and it does that several times to reach an actual steady state. And so how does this current stay sustained for more than just a blip? Because with this induction theory, we've got a single change in the electric field and changing current, change in magnetic field, kind of the step response, which sure we would expect it to induce a little rise and fall, a little blip in this wire, but that definitely doesn't explain the steady state that we see, or quasi-steady state. So that's one misconception. And another one that I've heard a lot in these explanations that more addresses how we can have extremely slow electron drift velocities on the order of centimeters per minute, but we can still have fast acting electrical circuits, right? We can flip our light switch on and nearly almost immediately the light bulb turns on. And so you'll hear it explained, or an analogy given, that okay, think of a tube with marbles in it, and it's filled with marbles, and you push an extra marble in one end, and immediately or nearly immediately you'll have a marble popping out the other end. And of course this explains how pressure waves move through solids or liquids or whatever, but that's not a great analogy for exactly how electrons are acting in a wire. First of all, we've got billions of electrons in even just a 1 foot length of 12 gauge wire. We've got like 10 to the 23 electrons, and additionally we're going to have the positive nucleus of the copper atoms, right, this copper lattice of the conductor. And what we're going to find is that basically if one electron starts to move in a certain direction, it's not going to produce this sort of chain reaction of, okay, it's going to hit another electron and so on and so forth. That might happen to its nearest neighbor, but basically over the distance of maybe a couple atoms, that direction, that velocity is not going to be preserved in that same direction. So it's not like we have this constrained 1D line of electrons where you would expect, if they're constrained to this one-dimensional line, then you're going to have this spring-like interaction between the electrons. But really it's kind of this sea of electrons in the conductor. So that's not a great analogy, but hopefully my explanation here will provide some better analogies and give insight into how it actually works. So I have the simulation here just before the switch closes, and you can see both sides of this wire are positive, and the ground or zero potential is this little section here. And if I step this forward, you can see the switch closes and this new potential is propagating outwards. And basically, we can continue this until eventually we see the electric field reach this wire opposite the source. And we can see the direction of the electric field is parallel with the load wire here. And most of these electric field vectors have some component that's parallel to the wire. And so we would expect, essentially, once this field starts impinging on the wire, that these electrons are going to be influenced by that field and are going to be accelerated accordingly. And that is actually what is responsible for driving this initial current that we see, is simply the electric field being pointed in a certain direction and driving electrons in the opposite direction, just by convention. And so that's kind of as simple as the explanation is, but I'll still dive a little deeper into the mechanisms that eventually establish a steady state current, because you might be thinking, okay, so if all it takes is an electric field to drive current, then that current is dependent on the distance that this wire is from the source, right? And that is actually true. In this initial current we see, if this wire were twice as close, we should expect to see a current that is 4 times as high, because electric field strength drops off according to the square of distance. And so that might kind of seem unintuitive, knowing that eventually this whole loop is going to have the same amount of current flowing through it. You might also be thinking of this unconnected wire here and be thinking, well, how could just the presence of this electric field be driving current? Because that electric field is always going to be present as long as the source is there. But we know that this current in the wire can't always be present, because in steady state, this random piece of wire hanging out here can't have a current flowing through it. And if we start to think, okay, as this field marches along and it's influencing electrons towards the extremities of the wire, sure, we do have a current flowing here, as we showed in the previous video, showing this case that it does have a current that matches the load up here. They look identical for the first transit time to the end and back. But as it's influencing electrons all the way out to the end, we can start to think of this end case here. So now we've got an electric field that's trying to accelerate electrons that are right at the surface of the end of this conductor, but we know that those electrons aren't just going to happily hop off of the conductor and continue to flow. They actually reach essentially a wall. They run into a wall at the end of this conductor, and what they're seeing is this potential energy barrier, where it takes very low energy to push them in anywhere in the conductor, but once they reach the surface, it takes a lot of energy to separate them from that lattice. And so you'll basically have electrons start to pile up, or at least the density will become greater on this end, and the opposite will happen on the far end, where we basically have excess positive charge due to the evacuation of electrons here, because they're not being replenished from the end, but they are being driven to the left here, away from the end. And so as that continues to happen, these electrons will basically pile up on one end, be vacated from the other end, and produce their own electric field, which will be pointing from the right to the left rather than from the left to the right like the source field. And eventually that will totally cancel out the source field. And so the electrons within the wire and on the surface will experience no net electric field, and they'll have no reason to continue moving, and you'll have that steady state of no current flowing in the wire, but it will be polarized. And so then you might have the question of, okay, by what mechanism does a steady state current get established in this loop? Because we kind of know the fate of this unconnected length of wire here, how it reaches its steady state, like we just explained. But what about the loop? Because it's a little more complicated, right? Its steady state is some non-zero value current, and we know that we're starting off with some reduced value of current, so how does that eventually get increased up to whatever the steady state happens to be? This happens through the interaction of surface charges. And surface charges are called surface charges because they are charges that reside on the surface of a conductor. And even in this case of this polarized wire, all those electrons bunching up on one end or becoming at least more dense on one end and the positive vacancies on the other end, those will all reside on the surface of the conductor, and that's just a property of the physics of the situation. It basically is a similar situation to when you have a conducting sphere and you add charge to it, and we know that the charge will all spread out to the surface of that sphere rather than being distributed within the bulk of the sphere. And this is just the lowest energy state possible. It reduces the potential energy of these extra electrons on the sphere. And so for similar reason, we have in wires, any excess charge is driven to the surface. And so that's why it's called surface charges. And what the surface charges do, the role that they play, is kind of analogous to the sheepdogs of the system. So they're the sheep herders, and if we think of the bulk electrons in the center of the conductor, or just in the bulk of the conductor, those are the what carry the bulk of the current, right? There's billions and millions of them, and we've got less that reside on the surface. But those electrons that reside on the surface, or vacancies, the positive charge, those essentially dictate what the electric field that the bulk electrons see. So that's why they could be called the sheepdogs of this system. And of course the source is kind of the sheep herder barking out commands to the dogs, which are the surface charges, which then kind of distribute that information to the bulk charges. And so that's how you can have a source, just a 1.5 volt battery, say over here at the center, and say you had wires even longer than this, way at the corner, you're going to have a very, very low electric field just due to that source, right? It's going to have dropped off so much, it's going to be nearly infinitesimal. But due to surface charges, they are going to establish their own field, which will eventually, in steady state, be sufficient to drive the same current in this part of the wire that's being driven right near the source. And so that's kind of an interesting thing to think about, something that I hadn't actually thought about much until making this video, and is actually, kind of highlights somewhat of a hole, I think, in the education of electrical engineering, or even just basic circuits, that I think could be taught better. Again, in steady state, we know that the surface charges must do their thing in such a way that they produce this constant surface charge gradient, which produces a constant electric field within the wire, which in turn produces a constant current. Right? We know that has to be the end state of it. But then there's still kind of this question of, okay, how do the surface charges decide this rate, right? If all they know up here initially is, okay, here's the electric field strength from the source, but eventually they even that out across the entire wire at some seemingly arbitrary value. And well, I can't give you an in-depth kind of analytical or numerical answer to that. It's basically the feedback mechanism that's driving these charges is such that they rearrange, and from that emerges the macro scale Ohm's law that we know to be true, which is a pretty simple equation, right, that we learn in circuits. And I say that the laws of physics that govern these surface charges, they produce Ohm's law rather than obey Ohm's law, right, because they don't have any agency, right? It's not like Ohm's law was created and then they have to follow it. It's basically this very complex interaction of these surface charges. From those interactions emerges what we have observed as a surprisingly concise and simple Ohm's law. And so that's pretty elegant to see that these very complex interactions produces a very predictable steady state condition that we can we can calculate the voltages, currents, power, and all that very, very easily. So like I said, I didn't really learn much about surface charges as far as their role in the system in steady state DC circuits, and I think that would have been useful to my intuition of how, even just this basic question of how does a bulb this distance from the source know what current should be flowing through it if the source field is dropping off with distance. And why isn't a bulb closer to the source brighter, right? So these pretty basic questions that are actually surprisingly difficult to answer, at least they were for me, with just the basic knowledge that I had learned through my education. But there are two authors, Bruce Sherwood and Ruth Chabet, and they actually authored a textbook, which I'll go ahead and bring up here. It's called Matter and Interactions, and it's a general physics textbook, but they have a portion on circuits and electromagnetism that I think does a really good job explaining basically what I just explained, but better and in more detail. So I would definitely recommend checking it out if you have the chance. And so they actually also have a paper that I've got here that they published back in 1999. It's called A Unified Treatment of Electrostatics and Circuits, where they kind of make the argument that pretty much what I was just saying, that the current way of teaching circuits leaves a lot to be desired when it comes to intuition. And so they propose kind of building up the theory from the basis of electrostatics, which will build this strong intuition. And here you'll see they kind of pose that question I just did of, why doesn't this bulb that's closer, why isn't it brighter because it's in a stronger electric field, and so on. And they give really good explanations of that. And so this book, Matter and Interactions, is basically a textbook that teaches electric fields and circuits here in chapter 18 from this basis of electrostatics. And so I would recommend checking that out if you can. And they also, you can see they've got a lot of neat visualizations of the surface charge gradients and densities and all of that, and the computational methods that they use to produce these they detail in another paper. It's actually fairly recent, 2018, 2019. It's called Computing and Visualizing Surface Charge Distributions. And it turns out that it's a non-trivial thing to do, and to do it analytically is pretty much impossible for very complex geometries. You can do it for some very simple geometries. So they're using a numerical method that's a modified version from the paper by Pryor here, and they're basically presenting this somewhat novel method of calculating these surface charge densities. And so it is also fairly interesting to me that it's a non-trivial thing to do, and there have been some recent I guess improvements in something that seems so old and basic. So I think it's worthwhile to read through, if not this fairly dense paper about the computations, at least the portions in the textbook that are, I think, very digestible and give great explanations, much better than I could do here in the video. So I would highly recommend that. And I did put together a very basic visualization that will hopefully give you some visual intuition. It's a quick animation I did in MATLAB. I'll go ahead and switch to that now. And what I have here, it's I wouldn't call it a simulation by any stretch of the imagination, because it's not simulating a numerically correct solution to anything. But I've got these little circles here that are representing electrons, or in reality, groups of billions of electrons right along a wire. And you can see here I've got 3 electric fields plotted. And so in orange we've got a source field from some source that's off to the left of the page, and it's negative, indicating that the vector would be pointing to the left. And then we have the surface charge field, which is that field that I was talking about that would be produced by this polarization of a wire, or just a gradient of surface charges that's going to have some electric field associated with it. And then in purple I've got the total field, which is just the sum of those, because based on the superposition principle we know that we can just sum the electric field at any point, and that will be the total field acting on any charged particles there. You can see that it'll start out with, of course, the source field being the only non-zero field present, because the electrons are at a uniform distribution initially. but as they're accelerated, the ones closer to the source with a higher field present are going to be accelerated more quickly, and therefore they're going to bunch up relative to the ones way out at the end are moving slower. And so we've got these guys that are moving faster than the one in front of them, and so they're going to get closer. And when that happens, you can see the surface charge field that is produced, and that summed with the source field essentially leads to a flattening of this total field. And that's kind of maybe the evolution of what it might look like in this transient situation we're talking about, where eventually a perfectly flat constant electric field will be present within the wire that will be influencing the bulk electrons that are conducting. So hopefully that's somewhat helpful in visualizing and building this intuition, but it's definitely not a complete explanation, and even reading through the book, you might have questions after that. And so, feel free to leave comments asking more exploratory questions, and if there's anything else big that I missed that it might warrant me making another video, I'd be happy to do that. And also, if you're interested again in the simulation results that I did in ANSYS, then go ahead and check out that video and check those out. And I think there I say, if anyone's interested in how to use ANSYS HFSS, I'd be happy to kind of do a walkthrough of how I made that simulation specifically, and that might be useful to a subset of the audience. So thanks for watching and sticking through this relatively long video. Hopefully it was useful, and I'll see you in the next one. Thanks.